Welcome to Chimas TV. Today we are looking at Taylor series. We are looking at Taylor series. Taylor series. In this lesson, we are actually trying to explain how we can carry out the Taylor series in the given model. And firstly, the general expression for Taylor series can be given as f of x equals to the summation of n from 0 to infinity. We have the coefficient and we have x minus a. All of this is the power of n. At this point, we can further expand the expression by looking at writing it this way: CO plus C1 into x minus a plus C2 x minus a raised to the power of 2. We have C3 x to the power of a raised to the power of 3 and plus C4 x minus a raised to the power of 4 plus this till infinity. So at this point, we'll try our best to make sure that we actually formulate a procedure of looking at the coefficient of Taylor series. So at this point, if we call this equation 1 and we find a point if your x equals to a and we substitute a in place of x, we are going to have c raised to the power of o plus c1 into this and plus c2 into a minus this plus c3 into a minus a plus c4 into a minus a raised to the power of 4. We realize that f of x into a is equal to c0. So we have actually substitute the value of a, which can be any number 1, 2, 3, 4, any number, in place of x. So we further look for the coefficient c1. Coefficient c1. How do we look for this? We realize that if you can differentiate the equation, let's see f prime, this is going to be equal to CO is going to be 0 because it's a constant. We have C1 plus 2 dot C2 into x minus a and plus 3 dot C3 into x minus a raised to the power of 2. We have 4 dot C4 into x minus 3. So by doing this, if we substitute f prime and substitute a in the x, we are going to have c1 plus 2 c2 into a minus a plus 3 dot c3 into a minus a raised to the power of 2. We have 4 dot c4 into raised power of 3. So when we substitute a in um, in place of x at x prime, we're going to have c1, coefficient 1. Furthermore, we do the same, f prime prime into x. We're going to differentiate f prime prime, f prime again to have f prime prime. So at this point, you are having 2 dot c2 plus 3 dot 2 dot c3 into x minus a. We have 4 dot 3 c4 into x minus this. So we realize that if we substitute x equals to a, we are going to have f prime prime into a, we have 2 dot c2 plus 3 dot 2 into a minus a plus 3 2 4 dot 3 dot c4 into x minus a. So at this point we realize that the value of c2, let's go to the next page, the value of c2 is actually equals to f prime prime into a becomes 2c2. So your c2 is f prime prime into a divided by 2. So we further differentiate the f prime prime 3 times. So we are going to have from our f prime prime, we are going to have that's 3 dot 2 dot c3 plus 4 dot 3 dot 2 dot c4 into x minus a. So when we substitute a in place of x, we are having this dot 2 dot c3 and this is going to be 0. So at this point your c3 is f prime 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 into f of a divided by 3 dot 2. So finally we carry out the fourth differentiation of f of x, and that is giving us 4 dot 3 dot 2 and dot c4. So your c4 actually becomes f raised to the power 4 times 6a divided by 4 times 3 times 2. So we can actually say hence f of x can be written as the summation of from 0 to infinity. In place of cn, we can use f of n, that is the number of differentiation into x divided by n factorial. We open the bracket, x minus a raised to the power of n. So in this case, you can actually conclude that um, f of x is equals to f of a plus f prime x f prime of a open bracket x minus a plus f prime prime into a minus divided by 2 factorial. You open the bracket minus a raised to power of 2 and f prime 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 into x divided by 2 factorial x minus a raised to power of 3 plus till infinity. So at this point, we've proven on how the Taylor series expansion can be analyzed for any individual for any individual expression. For example, we can have given that for example one on Taylor series, we can have that f of x is equals to x to the power of 2 minus x plus 1. Carrying out the Taylor series of this, we first of all look at the coefficients. So how we are going to do this? So we're going to look at this at x equals to 1. So at this point, we start by saying you write out the form approved formula, which is into n factorial x minus this. So at this point, we can realize that f of x of a, which is equals to f of 1 given, is giving us 1 raised to the power of 2 plus 1 plus 1, and that is 3. Hence, your CO is 3. So we carry out the first demonstration of um, f of x, which is giving us 2x plus 1. So when we introduce 1, x equals to 1 into this, we are having 2 into 1 plus this, and we still have 3. So we also carry out the differentiation 2 times, and the answer is 2. So being a constant, even if you introduce a, we're going to have 2 in the constant. So hence, the Taylor series expression being f of x equals to f of this plus f prime of this x minus a plus prime prime a divided by 2 prime this. So we have, so in this given model, we're having f of this, that is CO, which is 3, plus f prime of x, this is 3, and you are saying minus 1. 1 was given in place of a, and also f prime prime of this is 2 divided by this. So at this point we have this. So the Taylor series of that expression is 3 plus 3 into 1 minus this plus 2 into this reciprocal of 2 answers. So on that note, we can actually write out the series that will stand as a standard of the Taylor series, because if you do not do that, we will be confused. So we have the Taylor series standard expression for exponential. So for exponential expression, we have that e of x is from 0 to infinity, and we have this factorial. Also, if peradventure we have a minus x, is going to give us this, and we raise the power of n, we have that. And also we also have 4 sine theta and also 4 cos theta, different the same approach, and that will serve as a standard for further analysis on the respective function. Thank you as you listen to my next video.